Um, Welcome back to the deep dive. We have a stack of documentation on the table today that is, frankly, unlike anything we've covered recently.
Yeah, it really is.
It is highly technical, it's deeply philosophical, and it's a little bit unsettling once you really start to understand what it's actually doing.
I agree completely.
We are looking at a system today, an instrument really, called Structura.
Unsettling is probably a very good word for it. Because usually when we sit down to talk about computer vision or image analysis, we are firmly in the land of semantics.
Right.
We're used to asking the computer, what is this? Is it a cat? Is it a tumor? Is it a stop sign? We want labels. We want categories.
Exactly. We are completely obsessed with the what. We want the AI to just tell us the name of the object. But Structura doesn't care.
Not at all.
It doesn't care if it's looking at a picture of a kitten, a collapsing bridge, or just a randomized field of static. It genuinely does not care about the meaning of the pixels. It cares about the physics of them.
And that is a fundamental shift. It's moving from what is this object to how does this system behave? We are moving completely away from semantics and into the realm of structural dynamics.
Yeah.
We are treating an image not as a picture of things, but as a map of mathematical relationships and forces. And to really do that, we have to wrap our heads around a concept that is the backbone of this entire project.
The structural regime.
Exactly, the structural regime.
It sounds so intense, like we're talking about geopolitics or something. But in this context, we are talking about the invisible architecture of an image.
Right.
The idea is that an image isn't just surface-level colors. It's a data set that has an underlying posture, or an underlying health, if you want to call it that.
Think of it like a building. You can walk past a library and say, oh, that's a library.
Sure.
That is the semantic layer. You know what it is. But a structural engineer looks at that exact same building and sees something completely different.
They see the math.
They see load paths. They see tension vectors. They see compression and stress. They don't care about the books inside the library. They care about the integrity of the frame.
Yeah.
Structura is effectively that structural engineer, but built for digital data.
And what I love about this, speaking strictly from the developer side of things for a second, is the sheer elegance of the instrument itself.
It is remarkably clean.
It's so refreshing. I was digging through the repository, and we aren't talking about some massive bloated neural network trained on 5 billion copyrighted images that just hallucinates answers.
Not at all.
Structura is a pure mathematical instrument. It runs in a single Python process.
That is a crucial distinction to make right up front.
It really is. It uses standard scientific libraries. NumPy, SciPy. There are absolutely no external machine learning APIs here.
Right.
It's not calling home to OpenAI or anything like that. It is clean, rigorous, transparent code. It feels like a return to first principles in a lot of ways.
In a world of black box AI, where we often don't actually know why the computer made a decision, this is entirely transparent physics.
Yeah.
It is designed to measure very specific calculable things: spatial organization, fragmentation, and scale-dependent stability.
But before we get too deep into the mechanics, and we are definitely going to get deep today,
Yeah.
we have to address the core paradox that Structura is actually trying to solve.
The quote.
Yes. There is this quote from the documentation that I highlighted immediately. It says, "An image can appear orderly, yet exhibit scale-free instability signatures."
That is the crux of the whole project. That is the unsettling part we mentioned earlier.
Right.
Our eyes are easily fooled. We see symmetry, we see familiar shapes, and we think, oh, this is solid, this is organized.
Well, mathematical.
Mathematically, underneath the hood, that exact same image might be teetering on the edge of chaos. Structura is designed to see that invisible instability that the human eye just glosses over.
So our mission for this deep dive is to unpack exactly how it does that for you. We are going to look at how this tool acts like a combination of an X-ray, an MRI, and a CT scan for data.
It's a great analogy.
We've got 3 analytical axes and 6 structural lenses to get through.
It is a lot of ground to cover. But if you stick with us, you are going to look at digital images very differently by the end of this hour.
Absolutely. So let's start with the basics.
Yeah.
Section 1. What is Structura? And arguably more importantly, what is it not?
We really have to set the boundaries early here. Structura is defined in the documentation as a multi-scale structural regime analysis instrument.
Bit of a mouthful.
It is, but every word matters there. Multi-scale means it looks at the image at different zoom levels simultaneously, from the fine details all the way to the broad strokes.
Right.
And structural regime means it's categorizing the state of order or disorder.
And here comes the anti-pitch. which I think is totally crucial for managing expectations, especially with all the AI hype right now.
Mm.
Structura does not classify semantic content. It doesn't know what a building is. It creates a mathematical abstraction of a building.
Correct. And even more importantly, and this is a rigorous disclaimer, that the documentation makes very clear it does not detect disease,
Yeah.
and it does not diagnose structural failure in the engineering sense.
Right. You cannot take a picture of a cracked beam in your basement, run it through Structura, and have it tell you if your house is going to collapse.
No, it is not a magic 8-ball for safety. It measures statistical structural behavior.
Yeah.
It can tell you that the image of the beam exhibits scale-free instability signatures that are mathematically similar to the systems that are breaking down. But the interpretation, that remains human and contextual.
It provides the data, you provide the judgment. It's
Exactly.
like a thermometer.
Yeah.
A thermometer can tell you your temperature is 104 degrees. It cannot tell you if you have the flu or a bacterial infection.
Right.
It just tells you the regime of your body heat is in the danger zone.
That is a perfect analogy. It measures the state, not the cause.
Now, I want to geek out on the tech stack for just a second because I know we have some listeners who care about the how.
Let's do it.
This thing is built on Python and Streamlit. It uses Pillow for image handling, scikit-learn for some of the classification logic, and Matplotlib for the visualizations.
It is a classic scientific computing stack. It's the exact kind of stack you would see in a physics lab or a meteorology station.
It is.
Yeah.
And there's this one detail about Lanczos downsampling that really caught my eye. The system standardizes every single input image to exactly 124 pixels on the long edge.
Yes.
Why is that specific algorithm and that specific size so important here?
Consistency. In science, you have to control your variables. If you want to measure the physics of an image, like its entropy or its gradient flow, you need a standard reference frame.
Makes sense.
If you analyze a massive 4K image and then a tiny thumbnail, the noise profiles would be completely different just because of the resolution. The thumbnail would look mathematically smoother just because it lacks data.
So you really can't compare apples to oranges.
Exactly. By standardizing to 124 pixels using the Lanczos algorithm, you level the playing field.
Why Lanczos specifically?
Lanczos is chosen specifically because it is very good at resampling. It preserves detail without adding ringing artifacts or artificial noise. It keeps the data as honest as possible so that when we measure the instability, we are measuring the image, not the compression artifacts.
It's like making sure everyone is running the 100-meter dash on the same track with the exact same shoes.
Precisely.
Okay, let's get into the actual machinery. We mentioned there are 3 analytical axes. Let's start with axis 1, the static fingerprint or pattern classification.
This is the first pass. This is triage. This is about static similarity. Essentially, Structura is looking at the image and asking a very basic question. How much does this image resemble a known state of fragmentation?
And to do that, it needs a baseline, right? It needs a control group to compare against.
You're right. The developer created a specific training set for this instrument. On one hand, you have 100 images of organized grid block synthetic patterns. Think of a perfect chessboard, or a clean brick wall, or a wire mesh. That represents pure mathematical order.
And on the other hand,
You have 100 Gaussian filtered random field patterns. That represents chaos, or at least unstructured noise.
so Structura looks at your image and tries to place it on the spectrum between that perfect grid and that random noise. But it's not just looking at the pixels directly, it's extracting features. It's looking for specific telltale signs.
It extracts 6 specific multiscale features, and these are fascinating because they really break down what chaos actually looks like to a computer.
Let's run through them. First up is the Sobel gradient transition strength, which sounds like a sci-fi weapon.
It does, but it is a classic tool. The Sobel operator is an algorithm that detects edges. It calculates the gradient of image intensity.
Okay.
So transition strength is measuring how sharp the changes are. Is the image blurry and soft, like a fog, or does it have hard, jagged, violent edges?
Fragmented systems, things that are physically breaking, often have very sharp, erratic transitions. Next is the coefficient of variation scale dispersion. And this one is measured across 5 spatial scales: 2, 4, 8, 16, and 32 pixels.
Yes.
Why checking at 2 pixels versus 32 pixels?
This is the multi-scale part kicking in. The coefficient of variation is just a statistical measure of variability. By checking this at 2 pixels, then 4, then 8, Structura is asking, is the variation consistent as I zoom out?
Why does that matter, though?
Because nature usually scales somewhat smoothly. If you look at a tree, the texture of the bark has a relationship to the shape of the branch, which has a relationship to the trunk.
Right, there's a continuity.
Exactly. But in a broken or artificial image, you might see a huge variation at 4 pixels, lots of noise, but then it totally vanishes at 32 pixels. That mismatch is a major signal. It suggests the structure is superficial, it is not deep.
Then we have local variance, structural fragility, and intensity nuclei density.
Nuclear density is a very evocative term.
Mhm.
It is looking for hotspots. Imagine a piece of metal that is pitting from rust. You get these little nuclei of high intensity change, little dots where the metal is fundamentally failing. Structure literally counts those. A high density of these nuclei suggests the structure is being eaten away. It's a measure of rot, mathematically speaking.
Wow. And finally, Gaussian pyramid energy variance and cross-scale gradient consistency.
Cross-scale gradient consistency is the big one for me. It asks, do the edges line up? If you have an edge at the fine scale, a crack, a line, does it still exist when you zoom out, or does it disappear?
Stuff disappears.
If the edges vanish or shift wildly as you zoom out, that's inconsistent. It suggests the structure doesn't have true integrity across scales. A real crack in a physical wall usually exists at both the micro and the macro level.
So it takes these 6 features, throws them into a logistic regression classifier, and spits out a probability. But, and I love this detail, it uses an epsilon smoothing factor of 0.01 on the output.
Yes, I noticed that too. It's a great touch.
Why smooth the output? Why not just let it say 100%?
Because it prevents artificial certainty. Algorithms love to say 100% probability. They are inherently arrogant.
Very true.
But in the real world, nothing is 100%. By capping it, by adding that epsilon, the system is essentially saying, I am very sure, but I leave a 1% margin for error.
It's like a mathematical representation of humility.
Exactly. It acknowledges that the model is just a model, not reality itself.
I really like that. Epistemological humility encoded into the software. So Axis 1 gives us a probability that the image matches a fragmented model. But that's just the surface. Now we get to the heavy stuff. Axis 2, the heartbeat, stability and phase behavior.
This is where we leave the world of simple classification and enter the world of statistical physics. Axis 2 isn't asking what does it look like, it is asking is it stable?
And the core concept here is the scale-free instability signature. We need to unpack that.
Sure. In physics, scale-free means that a system behaves the same way regardless of how close you look at it.
Like fractals.
Similar, yes. Think of a coastline. It looks jagged from a satellite. Zoom into a mile, still jagged. Zoom into a foot, still jagged. That is scale-free behavior. Structura is looking for a specific type of scale-free behavior that indicates a critical state.
The tipping point between order and disorder.
Precisely.
And the first step to finding this is the JSD drift map. JSD stands for Jensen-Shannon divergence. What is actually happening there?
Imagine an 8x8 pixel window, a tiny square, just sliding over the image. For every single window, it calculates a histogram of intensities, basically a bar chart of how bright or dark the pixels are in that tiny little square.
Okay, got it. 32 bins, right?
Yep, 32 bins. Then it compares that local histogram to the global histogram of the entire image.
So it's asking, how different is this little patch from the whole picture?
Exactly. That difference is the divergence. If the local patch is just like the rest of the image, the JSD is low, it is compliant. But if the local patch is weirdly unique, like a sudden crack in a smooth wall, or a tumor in tissue, the JSD spikes.
The source material actually shows this JSD map. It's this green and yellow heat map. And the bright regions indicate high drift.
Yes, and it's really important to note here, bright regions indicate texture differences. They don't necessarily mean the thing is collapsing yet. It just means there is a clear deviation from the baseline. It is a map of anomalies.
Okay, so we have the map of anomalies. Now, how do we turn that into an actual stability metric?
Yeah.
Enter alpha. This seems to be the magic number for Axis 2.
Alpha is definitely the star of the show here. Structura takes the top 90% of those JSD values, the most extreme deviations, and plots them on a graph, specifically a log-log graph. Then it tries to draw a straight line through them. The slope of that line is alpha.
And this slope tells us the power law behavior.
Correct. And this is where the physics comes in heavily. In critical phenomena literature, which is the study of things like phase transitions, earthquakes, forest fires, the exponent of the power law tells you the underlying state of the system.
We have specific thresholds for alpha. Let's break them down for the listener, because this is how the tool actually judges the image.
All right. If alpha is greater than 3.5, you are in a stable regime. The anomalies are rare and they are small. The system is robust. The noise is dampened.
Okay? And if alpha drops to around 3,
That is the transitional zone. This is the danger bone. In physics, the number 3 often appears as a boundary condition. It suggests the system is balancing right on the edge. It's not fully chaotic, but it is no longer strictly ordered.
It's critical.
Exactly. It's critical. Small pushes can lead to big changes.
And if it drops below 2.8?
Near critical. The system is dominated by large-scale fluctuations. In a physical structure, this would be analogous to widespread fracturing. The chaos is taking over. The structure is mathematically unstable.
So Structura calculates this alpha for the whole image, but then it goes a step further and calculates a criticality index.
Which is just a fancy way of turning that raw alpha number into a clean 0 to 1 score using a sigmoid function. It makes it easier for a human to read at a glance. A 0.9 criticality is easier to intuitively grasp than trying to remember if an alpha of 2.75 is bad.
There's one more metric in Axis 2, the correlation length, or SHE.
This answers the question, how connected is the chaos? Structura samples pixel pairs at different distances. It checks if the pixels are correlated. Do they change together? It finds the distance at which that correlation drops off, specifically below 1/e.
So a high correlation length means what exactly?
It means the entire image is talking to itself. If you have high instability, a low alpha, and high correlation length, that is bad, very bad. It means the instability is coupled across the whole system. It is a global failure, not just a localized scratch.
It's the difference between a window breaking in a house and the entire foundation shifting.
Exactly. The foundation shifting affects everything. It is highly correlated failure.
That is a perfect segue to Axis 3, spatial heterogeneity. Because, as the source notes, a global average can be incredibly misleading.
Right. This is the Simpsons paradox of image analysis. You could easily have an image where 90% is perfectly stable. Imagine a beautiful blue sky. But the bottom corner of the bridge in the photo is absolutely disintegrating.
Right. The alpha for the sky is great.
Yes. If you just average the alpha for the whole image, the sky drags the average way up and you get a stable score, but that bridge is still falling down.
So Structura uses a hybrid Gaussian pyramid to solve this.
It sounds like sci-fi tech, but it's really smart engineering. It combines two views. Part A is the global Gaussian backbone, the big picture we just talked about, 4 levels downsampled. Part B is the local overlapping grid pyramids.
It literally chops the image into windows with 50% overlap.
And it calculates a local alpha for every single window. So instead of one global number for the image, you get a map of alphas, a stability landscape. You can clearly see the stable sky and the unstable bridge as totally separate regions.
And from this landscape, it derives 4 key indices. This is deep technical detail, but let's hit them quickly because they really explain how the tool thinks.
First is the heterogeneity index. This measures the variation of alpha itself. Is the instability spread out evenly or is it clumpy?
Okay.
Second, critical nucleation fraction. What percentage of the image has an alpha below 3? Essentially, how much of the image is melting?
Melting is a very vivid image.
It's apt, though. When a solid turns to liquid, it loses structure. That is what we were seeing mathematically. Third is the localization score. Are the bad spots clustered together? If they are clustered, that is a nucleation site. It's a wound. If they are scattered randomly, it might just be sensor noise.
And finally, effective criticality.
This multiplies the nucleation by the localization. It acts as a filter. It prevents false alarms. If you have a few random, unstable pixels, high nucleation, low localization, the overall score stays low. But if they cluster high localization, the score spikes.
It really is trying to mimic the way a human expert would look at a scan. You don't panic over a speck of dust, but you absolutely panic over a tight cluster of cracks.
Precisely. It mathematically filters out the noise to find the actual signal.
Okay, we've covered the 3 axes. That is the foundation. Now we get to the part that feels like a detective's toolkit. The 6 structural lenses.
The documentation calls this research mode. The philosophy here is that structure is a compound instrument. You don't use just one lens to look at complex data. You need multiple perspectives to understand the truth.
Lenses 1 and 2 are the Gaussian global and local views, which we essentially just covered. That's visualizing the alpha maps. So let's jump straight to lens 3, the Laplacian lens.
The Laplacian lens reveals scale-specific discontinuities.
In plain English.
Structural stress lines. The math involves a 5-level Laplacian pyramid, basically subtracting an upsampled, blurred version of the image from the sharp version. What is left behind are the edges and the rapid changes.
The visual for this one is described in the docs as really striking. It's a dark image with glowing purple and pink outlines.
That glow represents structural stress. And it's weighted across scales, so a faint line that only appears at 1 microscale might fade out. But a stress fracture that cuts through multiple scales will glow brightly.
It highlights the faults.
Yes, it shows you exactly where the image is tearing.
Lens 4. The phase slip lens. This one sounds straight out of Star Trek. Captain engaged the phase slip direct.
It totally does, but it's actually measuring directional divergence. Here's the concept. Imagine an edge in the image, like the vertical side of a building. At a fine scale, zoomed way in, it points exactly north. Now zoom out. Does it still point north? Or does it twist to northeast?
So if it twists, that is phase slip.
Exactly. The formula involves 1 minus the absolute value of the cosine of the angle difference. If the slip is high, it means the structure is losing coherence as you zoom out.
It's deforming.
Yes, it's twisting or deforming across scales. A solid structure should be directionally consistent. If the microstructure points one way and the macrostructure points another, there is internal torque.
Lens 5. The structure tensor lens. This is all about alignment.
This uses a matrix called the structure tensor, denoted as J. It calculates eigenvalues, lambda 1 and lambda 2. Don't worry about the linear algebra. Worry about the output. Anisotropy.
Anisotropy just means direction dependent, right?
Yes. If you have a region where all the stress is lining up in one specific direction, that is high anisotropy. In the visual output, these are the bright yellow regions. This is incredibly dangerous.
Because it's focused.
Exactly. Random stress is one thing. Aligned stress means the system is preparing to shear or crack along a fault line. It is focused energy. The lens also checks coherence.
And finally, my absolute favorite name in the whole project, Lens 6, the crackling lens.
This is directly inspired by crackling noise physics. This is a real fascinating field of study. It looks at things like the sound of crumpling paper, or earthquakes, or magnetization in metals. These are systems that don't move smoothly. They move in jumps or avalanches.
So how on earth does a digital image crackle?
Structura detects discontinuities, breaks in the pattern. It filters out the small stuff and looks at the distribution of the big breaks. Then it runs a very specific mathematical test. Does this distribution look like a log-log power law, or does it look like a semi-log exponential curve?
And if it's a power law?
If the power law r squared exceeds the exponential by 0.1 or more, then it's classified as crackling. It means the system is capable of pseudo-events of any size. It is volatile.
Wow.
If it's exponential, the large events are rare and suppressed. But a power law distribution means a massive avalanche or total structural failure is statistically possible.
And there's a speckle check built into this one too, right? To make sure it's accurate.
Yes. To make sure it isn't just detecting digital image noise speckle from a bad camera sensor, it checks the ratio of high frequency to mid-frequency energy. If the ratio is above 0.6, it flags the result as unreliable, again, protecting against false alarms.
So we have all these lenses. We have stress maps, phase slips, crackling events, alpha maps. Section 6 is about integration. How do we actually make sense of all these separate signals?
This is the so what section of the tool. You cannot just look at one map. You have to overlay them.
The developer uses cross-lens integration. For example, there's a metric called active fragmentation,
which is defined very logically. You need an alpha below 3, which is instability ND. You need more than 10% of the image showing stress above the 80th percentile. It is an AND condition. Both must be true to trigger the flag. It confirms the signal from two different directions.
And directional stress is another one?
That's the overlap of the stress map from the Laplacian lens and the coherence map from the tensor lens. If you have a stress line that is also highly coherent lined up, that is a major structural risk. It's not just a crack. It's a crack that knows exactly where it's going.
And this all feeds into the final metric, the coupled risk score.
Yes. It is a weighted formula. 0.4 times the change in alpha multiplied by stress, plus 0.3 times stress multiplied by anisotropy, plus 0.3 times effective nucleation multiplied by coherence.
We don't need to memorize the formula, obviously, but look at what it actually values. It values the interaction of factors.
Exactly. Stress alone isn't enough. Stress times anisotropy is the problem. Nucleation alone isn't enough. Nucleation times coherence is the problem. It categorizes the image into low, moderate, elevated, or high risk based on these complex interactions.
But, and here is the crucial expert caveat, what is this score actually telling us?
It is a regime indicator. It is not a prediction of the future. It tells you the current thermodynamic state of the image. It does not tell you that the building in the picture will fall down tomorrow. It tells you that the visual data provided exhibits the mathematical signatures of a system near a critical transition.
It's describing the weather conditions, not the lightning strike itself.
That is the perfect way to look at it. It says conditions are favorable for a tornado. It does not say there is a tornado right there.
Moving on to Section 7, operational modes. This thing isn't just a basic script you run once. It has different ways of working depending on what you need.
There is quick mode versus research mode. Quick mode just checks axis 1 and the critical map. It's fast. Research mode fires up all 6 lenses and takes significantly longer to compute.
Then there is the physical capture consistency indicator. This one is really cool. It seems entirely designed to spot fakes.
Or heavily overprocessed data. Real physical light captured by a camera sensor has a certain messy entropy to it. It has heterogeneity. If an image is too perfect, if the heterogeneity is below 0.15 or the scale entropy is above 2.0, Structure flags it.
It knows it's unnatural.
Yes. It says, this looks too clean to be real. It is an anti-smoothing detector.
Monitoring mode is next. This tracks structural drift over time and creates a JSON history.
This is vital for long-term analysis. You don't care about one bad reading on a bridge. You care about the trend. Is the alpha dropping week over week? And the smoothing prevents phase flip-flopping, where the status jumps between stable and unstable just because of minor lighting changes.
And phase space compare mode.
This plots 2 different images on a graph. Alpha on one axis, correlation length on the other. You can see quadrants. Top right is organized and stable. Bottom right is fragmented and near critical.
So you can track degradation visually.
It allows you to visualize the entire trajectory of degradation. You can watch an asset literally move from the safe quadrant to the danger quadrant over time.
And finally, the mode that I personally want to play with. Live satellite mode.
This is brilliant. It pulls imagery straight from public NOAA, goes east and west satellites via CDN, no API key needed. It just grabs the latest Earth observation data, downsamples it, and runs the structural analysis in real time.
You could literally watch the structural regime of a hurricane or a massive cloud formation evolve live.
Or the structural regime of the data feed itself. If the satellite sensor starts failing, Structure would likely pick up the crackling noise in the signal way before a human eye noticed the digital artifacts.
That is absolutely wild. It turns the whole world into a data set to be measured.
It really does.
So let's wrap this up. We've unpacked the invisible architecture. We've looked at the math of order and chaos. What is the ultimate takeaway here?
Structure is a tool for seeing tension. We are used to seeing things. Structure sees tension. It sees the mathematical stress that exists between pixels, between scales, and between gradients.
It's not about meaning, it's about behavior.
Right. It measures regime behavior. The interpretation of that behavior remains human. But it gives the human a completely new set of eyes. Eyes that can see into the 4th dimension of scale and probability.
And I want to leave the listener with a thought that came up while I was reading through this. We've been talking entirely about images today. But images are just static 2D arrays of data.
Yes, fundamentally.
If we can measure the criticality of a static image using power laws, if we can confidently say this image has an alpha of 3 and is near critical, what happens when we apply this exact same math to other forms of static data?
That is the billion-dollar question.
Could a text document exhibit scale-free instability? Could a massive block of source code have an alpha of 2.8 just before it introduces a catastrophic bug?
Could a complex legal contract show structural stress in its clauses? Could a static financial ledger show crackling behavior right before a market crash?
Exactly. We are distinguishing between visual order and mathematical stability. Just because code looks clean or a contract looks standard doesn't mean it isn't mathematically balancing right on the edge of chaos.
Structure proves that the invisible architecture is real. The question is, what else can we point it at?
Something to really think about. Thanks for diving in with us.
A pleasure.